Today we're going to begin discussing Artax, or Bayesian Deconvolution. The idea here is to perform some quantitative analysis of our spectrum. The first thing I do is I open up the Artax program. Now, the default setting is that there is no password. You can change a password if you would like by selecting Change Password. Now, generally speaking, you will get errors as a consequence of the fact that you do not have an Artax system currently present. Likely, if you do have an Artax system present, this can be very useful. But for analyzing data from the tracer, these error messages are not relevant. Now, the first thing I do when I open up Artax is I want to begin to start a project. So I go Project, New Project. This creates a file bar menu over here. The very first thing we have is a folder named Objects. If I select the Spectrum tab, I can return to the grid that I saw earlier. I left click on Objects and I select Add Node. This gives me the opportunity to select a name. For reasons related to data analysis, the first word of every node name should be points with a capital P. So I will select points with a capital P. From here on, I can name my file anything. So in this case, I will call it Obsidian Test. And then I click OK. Now you see over here there's a little plus sign by the Objects menu. If I click it, I can expand to see the points folders I have created. You can have many different nodes and folders in this area. In fact, many people will use this as a database. So I can select and add another node and go through and add Spectra to this separately. These can be with any parameters, any object. In fact, some people will make sure that their Artax file has all the spectrum they have collected with our object for very easy qualitative analysis. In this case, though, we will stick to only one node. The next thing I want to do is go File and Open Spectrum. And I will select an area to analyze. So in this case, we will go to Artax session, and then Obsidian Cal Data. This will present our Obsidian Calibration Reference Library, which you can see here. Now note, you want to select the type of file you want to analyze. Many times when you first open Artax, the option will be spectra.spx files. Here you want to select down here and select tracer file for PDZ files. If I wanted to see text files, I would then select and see text files. In this case, I'm going to select all the tracer spectra I currently have available. I select them all by pressing Ctrl A, and now I click Open. You'll see here many different changing names, and when it's done, I will have every spectrum present on my screen at once. In this case, I have about 40 different spectra available. If I want to, I can add them all to my index system here. I select the points folder, I right-click, and then I select Add Spectra. Now, you see that same plus sign over here. When I expand, I can see every spectra that I currently have. You can hold up to about 100 spectrum at a time in this navigation window for the spectrum. In this file system, you can have thousands and thousands of different spectra, and it'll actually read in the spectra and regenerate them in this program. So you're not affecting the original spectra files. They'll be in the folder just where I left them. But by adding them to this window, it essentially duplicates and copies those spectra to this file. Now, to manipulate my spectra, I need to press and hold the Control button. I do so, and when I click, I can now spread. And you see the arrow button changes to these 4 arrow buttons. I move left to right to expand left to right. I move up and down to expand up and down. If I zoom into a port of the spectrum, I can then click below the x-axis to drag over to the right and then navigate peak by peak. If I ever want to return to my home view, I just double click. That is the navigation system in Artax. It takes a second to get used to, but once you're going, you'll be able to manage it relatively easily. Now the next thing I'm going to do is a little scary. I'm going to select this X button and close all of my spectrum. I do this because now I can bring up 1 spectrum, 2 spectrum, 3 spectrum, and select whichever spectra I would like to make a comparison. So here you can see that for this element, I can see the range of different potential values. My spectrum in green down here, which is Cannonball, has almost no detectable strontium, whereas my pink spectrum, Inman Creek, and my red spectrum, Archibarca, presents a slightly higher, much higher concentration. For this example, I want to use only one spectrum at a time. In this case, I'll start with Archibarca. What I want to do next is create a method for analysis. So up here, I can, for example, navigate to different existing methods. But many times, I won't have a method that already exists. The 3 buttons up here that are relevant are the Edit Methods button, the Periodic Table button, and the Bayesian Deconvolution button. To begin with, I'm going to open up the Methods Editor. Now the Methods Editor has 4 different tabs. The Measurement tab is only relevant if you're using an Artax unit. The Corrections tab is relevant regardless of what type of spectra you're looking at. Identification lets you select the elements, and Quantification lets you apply calibration. In this case, it only works if you create a calibration file in Artax, which won't be the subject of today's lecture. When I select corrections, I want to make sure escape and background are checked. I do not want to select shelf. That's specific to the Artax unit. Cycles refers to how many iterations or stripping cycles we will run through. In this case, a lower number, 10, is a little better. I then select a range of start and end kiloelectron volts to analyze. Because my spectrum down here goes all the way to 40 keV, I want to select 40, so that way I'm capturing the full spectrum. If I select identification, I can choose preset list, and now I see a periodic table. For now, I want to leave my periodic table blank. I now give my method a name. We'll call this Obsidian Example Test. I will add it. Make sure Calculate Concentration is not selected. I will then add the new name to the list, and there I see it down there. And then I click OK. Now, nothing fundamentally has changed, but what I can now do is begin a Bayesian deconvolution of the spectrum. I click on the periodic table, and I can now zoom into a peak. Now, by the way, one quick navigation tip. If I select the peak with my cursor, press the Control button, and then press the right arrow button on my keyboard, I can expand slowly to that focus point. If I want to contract, I press the left arrow button. Now, I click on the peak in question, and here in my periodic table, it gives me a list of possible elements this could be. Because I can see iron, I'm going to select iron as a label. Now, if I want to deselect iron, I deselect it from the periodic table over here. I can also just select iron here as well from the very beginning. Notice when I select and deselect, I change the color of the peak. This can be useful for qualitative analysis. If it's hard to see the color that Artax automatically gives you, you can easily change it by re-clicking on the element on the periodic table. Now I'm going to create a Bayesian deconvolution. When I do this, I'm going to create a blue spectrum that simulates what my spectrum would look like if only that element were present. So keep in mind, the red spectrum is my empirical data from the tracer. The Bayesian deconvolution will be a blue simulation of that spectrum. I click, and now you see a blue spectrum fitting pretty nicely over the iron peak. You can see my K alpha here and my K beta over here. Note as well that the K alpha and K beta lines are highlighted in the same color for this element. Also note that while I'm matching my peak for iron, over here I have a different peak that is not represented. The Bayesian deconvolution only uses the elements that you select. This is a manual deconvolution. So the computer won't do the hard work for you. It can if you select the auto-identification button, but the computer is no replacement for your judgment. I strongly recommend go through and select the elements that you believe are present. If I navigate over here, again, I'm clicking below the x-axis and dragging from left to right to navigate. I can click on the peak that shows up over here that iron does not explain. And it gives me the option of copper. I select copper, run the deconvolution, and now this peak fits. If I come over here though, I see a blue peak where copper has a K beta at. It doesn't fit very well. But I see over here, if I click this spectrum, or this peak, this is where zinc would occur. Now, the software is not going to make a judgment call. You can see that both zinc and rhenium are possible elements. In this case, zinc is much more common. So I select zinc, I run the deconvolution, now both peaks fit a lot better. If I look very closely, and here I navigate up, I see there's a very small peak over here that is not captured by the Bayesian deconvolution. I click there, and I see that it is gallium. Now, without a Bayesian deconvolution, it's very hard to notice this small peak. But when I draw the Bayesian deconvolution, I can see that there's clearly a peak above my background area. What I find that Bayesian deconvolution is very good at is finding invisible gorilla elements. Now, the invisible gorilla is a term that comes from a psychological study that occurred a few years back. A professor took a number of students and had them watch about 30 seconds of a YouTube video of a basketball game. The students had to take notes on the performance of each team. At the end of the 30 seconds, they had to take a brief exam that tested how well they paid attention. They were asked how many assists, what are the score, which team presented a better defense, etc. The last question was, at what time did the gorilla walk in the middle of the basketball court? The students were very confused by this. About 80% had no idea what this question referred to. They then rewatched the video and saw that 17 seconds into the game, a man in a gorilla costume walks out in the middle of the basketball court, thumps his chest, and then walks off. Why did the students miss the gorilla? Well, it's because they were so focused on the elements that they expected in the spectrum that they missed those elements that were not present, that were not immediately obvious. When you're over-focused on what you think should be there, you very often miss what is there. In this case, we have a very small trace of gallium present, and it's very easy to recognize that it's present because of this Bayesian deconvolution. I can now run my deconvolution with gallium selected. I run the deconvolution with gallium selected, and my peaks now fit much better. I keep navigating, and I select those elements that may be present. In this case, this element could be either arsenic or lead. I'm first going to select arsenic. And I see there's a peak here, but there really isn't any other peaks. If I select over here, there's some bromine. There we go. Fits much better. I select over here, but now I have a problem. This could be either lead or it could be krypton. Now, krypton is a noble gas over here on the periodic table. It's highly unlikely that this is krypton. If I select lead, run the deconvolution, I see that lead could be present. But I still have another peak over here. I select here, perhaps this is thorium. Now I'm very far off. If I see over here, these peaks don't match. I select this mismatch, and I see that this could be rubidium. If I run the deconvolution, now things fit much better. Lead, bromine, thorium, and rubidium all broadly agree with the spectrum I'm looking at. I then select strontium, zirconium, and I continue selecting those peaks that match the spectrum. Niobium. Over here, I have rhodium, and I have palladium. These elements are absolutely present. Rhodium is the X-ray target in the tracer model I'm using, and palladium is used as the collimator for the X-flash detector. If you look, you'll see a big mismatch right over here, roughly between 18.5 keV and 19.5 keV. This area is the Compton peak. This is the inelastic scatter, whereas the rhodium peak is the elastic scatter from my target. In this case, the photons from rhodium are bouncing off of the light elements present in the sample. Because this is obsidian, the most dominant element present is oxygen. So there's a lot of opportunities for those rhodium photons to lose energy. When they do so, they fall into a big pile here, and that forms my Compton peak. The deconvolution will never fit the Compton peak very well. But don't worry about it. It's not going to significantly impact your results. Rhodium and palladium, however, must be selected, or whatever your target happens to be, if it's molybdenum, silver, etc. The goal with the Bayesian deconvolution is to identify every element that's present to provide every opportunity to do successful interelemental corrections for each net intensity peak. I keep coming along over here. Here I find a tin line. If I continue, here's a little bit of an element. That's barium. Note that the barium also fixed this small peak down here. That looks to me to be about everything we've got. So I'll now go back, double check, and make sure I get the light elements as well. Here we have manganese. Here, just a little bit of chrome. Here, I have a potassium line, but over here, because I used the green filter for this data collection, my sensitivity to light elements is not very high. But in any case, I look at this and I see a spectrum that's broadly working. I see potentially one element, nickel, just about at the limit of detection. Now that I have a decent Bayesian deconvolution, I come back up to my methods editor. I come to the identification tab, and now I select Get Elements. When I click this button, all the elements that I selected from a Bayesian deconvolution are present here. I can now replace, OK, and now I've updated my methods. Now I do something kind of scary. I'm going to delete the spectrum. And when I do so, I lose all the elements I just went through the trouble of generating a Bayesian deconvolution for. Now I select a new spectrum, in this case KES362, a volcano from Kenya, and we'll try the deconvolution here. Now, when I click the Bayesian deconvolution button, it will apply the Bayesian deconvolution to this spectrum. And it will use all the elements I selected the last time. I click it, and I generate my deconvolution. I now expand and double check to make sure I've gotten all the elements that may be present here. Here, I have a little bit of a misfit there. So I double check, and that turns out to be yttrium. There, fits better. If I zoom in down here, do you see this little shoulder off of rubidium? That is actually another element. If I select that area on my periodic table, I see that that is where the uranium L-alpha line will fluoresce. I select uranium, I run the deconvolution, it fits just a little bit better. Now, that's a very small difference. How confident can I be that there's actually uranium here? Well, here I'm cheating a little bit because I do know there's uranium in this sample. We've actually had this analyzed using neutron activation analysis, and we know there's about 30 parts per million of uranium. We also know that since it's coming from obsidian, and thus is a representative at least partially of the magma underneath the Earth, that there's a set ratio between uranium, thorium, and lead, provided contamination is not a strong possibility. There should be a statistically significant relationship between uranium and thorium, but we can test that assumption with the next step. Now, so far, I've built a small database, and I've applied a Bayesian deconvolution. Now that I've updated that deconvolution with the new elements that I've found, I can apply that deconvolution to every spectrum present in this sample. So, I click on the points folder, I select Analyze, and I evaluate results. And this applies the Bayesian deconvolution to every single spectrum in this folder system. It doesn't matter if you have 2 spectra or 2,000 spectra, you will be able to analyze all using the same method. When it's done calculating, I can now select Export Results to Excel. When I do this, it'll give me the opportunity to create a spreadsheet. In this case, I'll name my spreadsheet Obsidian Test, save, and it's going to write this Obsidian, the net intensities to an Excel spreadsheet. I now minimize, and I look for the new spectrum. I saved it to the wrong spot. So let's go Export Results to Excel. It's in the Artax session folder. You always have to remember exactly where it is you save. So here I have my Obsidian test results. I open up. The first sheet, parameter, has all the different parameters used. The elements, the corrections, the filter, the energy, and the deconvolution method. In this case, a Bayesian deconvolution. I select points, and here I have each element and the net intensities for each element. This is essentially the number of photons that would explain this element's manifestation in the spectrum. I also have a little file handle here. You can actually very quickly erase this file handle using basic functions in Microsoft Excel. So I find, select, replace the name with nothing, and I can clean up those names just a little bit. Now I can do a little bit of analysis. If I want to see which elements have higher or lower concentrations, I can do that here. So for example, if I select iron, insert column, I can see a column plot that shows which of these samples has more or less iron present in that obsidian. Now, remember earlier we were discussing uranium. With uranium, we had only a small difference. Here in Artax, you can see it. If I run my deconvolution without uranium, it's only a narrow shoulder. If I run it with uranium, I see it fit a little bit better. But do I really have uranium there? Well, I can select my uranium L line and my thorium L line, and if I am seeing uranium, I should see that the higher concentrations of uranium roughly correspond to the higher concentrations of thorium. Insert, scatter. In this case, even though I have a number of values that are 0, I see a weak relationship between uranium and thorium. Add trend line, display equation, r squared. Here I see I have an r squared of roughly 0.2. I can also test this with thorium and lead. Insert, scatter. I can see there's a little bit stronger of a relationship, likely because it's much easier to see both lead and thorium in the same spectrum. In any case, this is how we're able to do semi-quantitative analysis. Now I say semi-quantitative because, strictly speaking, these aren't parts per million, they're not concentrations, they're just a processing of the spectrum. You can create a quantification using this data by using the net intensities and known values. For example, in an earlier case, I ran a deconvolution of potassium in olives. So in this case, I have my net intensities for potassium and my known concentrations of potassium in the olives. I then regress the net intensities per second by the actual concentration in the plant, and I see that I get a very strong relationship. I can essentially create a simple calibration curve using this approach as well, which I can then use to analyze other data in a quantitative manner. However you choose to use these data, semi-quantitatively or quantitatively, you have that option. It may also be advisable to use the spectrum itself as evidence for a hypothesis. In this case, let's say I want to save this spectrum. I come up to Export, I can copy graphic, and then I can paste that graphic in a file. Let's come back to the Obsidian test. So here, I can save a copy of this spectrum and paste it wherever I would like to do so. I can also change, if I wanted to see the whole spectrum, export, copy graphic, I can do that as well. So whatever my screen view is, I can essentially capture that screen and use that to make a qualitative demonstration of the same principles. This concludes our short tour with our Artax. In general, the Artax software is very good for three things. The first is building a database. The second is for applying a Bayesian deconvolution. The third is for allowing you to perform semi-quantitative or quantitative data analysis. If you have any questions, please contact an application scientist at Broker Elemental. But in any case, we hope that this gives you a brief tour of the functionality of the Artax software. Thanks for your time, and have a good day.